Mass losses from glaciers and ice sheets are currently the main contributor to sea level rise, and this contribution is expected to increase in the forthcoming decades and centuries.
Within the European Commission-funded project INTAROS, our team, formed by researchers from Universidad Politécnica de Madrid and from the Geological Survey of Denmark and Greenland, GEUS, is investigating the mass losses of marine terminating glaciers and ice sheets.
To simplify the presentation, let us assume that the marine terminating part of the glacier is not floating, as shown in the cartoon. The mass losses at the glacier front are referred to as frontal ablation. It includes iceberg calving, submarine melting, and melting and sublimation at the emerged part of the glacier front. Frontal ablation as a whole is often approximated by the ice discharge through virtual flux gates defined near the glacier front. The flux of ice through such flux gates is referred to as solid ice discharge or simply ice discharge. The meltwater produced at the glacier surface reaches the bed through crevasses and moulins and flows subglacially towards the fjord. This freshwater flux entering the fjord is commonly known as subglacial discharge, and it will be a key control on the submarine melting of the glacial front.
We use two regional climate models, or RCMs, Rahirhan and MAR RCM. These provide the water inputs. That's both melted ice and also snow and rain on the ice. At GEUS, we have developed a solid ice discharge and a liquid freshwater runoff product to meet these needs.
From the INTAROS solid ice discharge dataset, the link takes you to the GEUS Dataverse.
We've seen how to obtain the freshwater and solid ice discharge. Now we'll see how to use numerical approaches to estimate the partitioning of ice discharge into iceberg calving and submarine melting.
To build the numerical model, we first need to identify the different components of the system which are subject of simulation. In our case, we should think in two components: the ice one, which is the tidewater glacier, and the ocean one, which would be the fjord where the glacier ends to. For the glacier model, we use the software Elmer Ice, which is based on the finite elements method. For the ocean components, the software MIT GCM, which is built on the finite volume method, is used to solve the fjord circulation model, while a MATLAB routine is used to simulate the buoyant plume model. How can we obtain information about the glacier fjord system as a whole? We need to couple the different components to obtain a single ice-ocean couple model. To evaluate the goodness of our couple models, we show here the model performance against the observed propositions. Here we see the submarine melting taking place at different depths of the ice front for every week of the simulation. We obtained that submarine melting represents between 60 and 70% of the discharged ice, while calving accounts for 30 to 40% of that ablated area.
We have seen how INTAROS data catalog can be used to download data on solid ice discharge and meltwater runoff, and how can models be used to separate frontal ablation of ice discharge into its two main components, iceberg calving and submarine melting.